Our homeworld, the Earth, is a terrestrial planet. The terrestrial planets are the four smallest and innermost planets of the solar system. They are small and rocky, and for the most part, pretty boring. Further out, beyond the asteroid belt, 4 more planets orbit the Sun. Gas giant planets. Massive, continuous chemical reactions of extreme weather, which drives a range of fascinating phenomena, including the formation of majestic patterns across their upper atmospheres and rich subsystems of moons and rings. In our solar system today, there are 4 of these gas giant planets. Jupiter, the oldest and largest of the planets. Saturn, home to a magnificent ring system. Uranus, a cold, atypical world. And lastly, Neptune, the most distant of all. But before we take an up-close look at these worlds, what do we actually mean by the term gas giant? The term gas giant was originally coined by science fiction author James Blish in 1952 in reference to all the large planets in the solar system. We didn't really know much about our own gas giant planets, let alone extrasolar planets back then, and so in the years since the meaning has been refined somewhat. A gas giant is a comparably large planetary mass celestial body with a rocky or molten core, but topped with thick layers of hydrogen and helium in different states, the same elements which are present in young stars, which is why some gas giants are known as failed stars. The gas part of the term refers to the hydrogen and helium within the planet, but it is actually kind of inaccurate, because the vast majority of a gas giant's matter is not in a gaseous state. Instead, the pressure below the outer atmosphere is so intense that most of the matter has reached what is known as its critical point, the point for a substance at which the distinction between a liquid and a gas disappears. These huge, pressurised planets tend to be at least 2 or 3 times bigger than the Earth, and dozens of times more massive. They can also grow to be much larger, but it's worth noting that size doesn't correlate with mass in this case. Heavier gas giants, which exert a stronger gravitational influence, will keep themselves pulled together more tightly and compactly, making them smaller than cooler, lighter gas giants. In any case, they have vast upper atmospheres which drive extreme weather, which marks the surface of each planet with bands, spots, and other fascinating features. But then, why have these planets been able to grow so large and become so different if their cores are made of the same stuff as the inner planets? Well, the answer to this has a lot to do with the planet's starting position. Gas giants begin life as large, rocky planetary cores, which grow larger and larger through the accumulation of mass as they move around their system, kind of similar to the way in which the terrestrial planets formed. The difference, however, is that these planets formed beyond the snow line of the solar system, the boundary beyond which it is so cold that water and other volatile substances can exist as a solid which is as hard as rock, and this provides loads of extra material for planetary formation. As such, these cores sweep up lots of matter and become massive in every sense, so much so that their gravity begins to attract hydrogen and helium gas, even more so if the star system is young, where hydrogen and helium clouds are abundant. This accumulation of gas begins to form an envelope layer around the planet, which becomes so heavy and pressurised that the rocky surface of the planet is transformed, turning the whole thing into a massive ball of liquefied gases in various forms under unimaginable pressures. Gas giants like Jupiter and Saturn are thought to consist mostly of hydrogen and helium, with heavier elements making up only about 10%. These heavier elements may be contained at the core, but are under such high and intense pressures that their properties at this depth are likely to be poorly understood. In contrast, the 2 other giants in the solar system, Uranus and Neptune, are quite different in size and composition to their older gas giant brothers, and so warrant their own classification, the ice giants. This far away from the parent star, heavier volatile substances like methane, carbon dioxide, and ammonia can exist in a solid form, referred to as ices. Uranus and Neptune are composed primarily of these volatile substances, with the majority of the mass being contained within a thick, water-rich mantle layer of ammonia and methane. The methane at the surface is what drives the aesthetic blue colouring in both planets. Ice giants tend to be smaller than gas giants, but their mass is still sufficient to create diamond rain, diamond icebergs, and many other incredible phenomena below their surfaces. And, whether it's a gas or an ice giant, both are massive enough to attract moons, and plenty of them. Most gas giant planets have dozens of satellites, with some large enough to be classed as planets in their own right were it not for their orbit around their gas giant host. And nowhere is this more evident than the solar system's godfather planet. Hydrogen and helium gas is prevalent across space in young star systems, which, along with the multitudes of rocky material, makes them perfect environments for gas giants to spring up almost as soon as the system's star begins to shine. The story was no different in our solar system 4.5 billion years ago. Jupiter was the first planet to form, and it remains the oldest and by far the largest planet in the solar system. After forming, it spiralled inwards towards the Sun, accumulating most of the rocky material in its path, allowing it to become far larger and heavier with less left over for the terrestrial planets. One of the reasons Mars is quite small compared to the Earth and Venus. We're still trying to understand this gargantuan planet's structure. One hypothesis is that its core may not be rocky, but a very dense liquid centre surrounded by layers of hydrogen and helium. Its gaseous upper atmosphere encases a layer of liquid hydrogen below, but further down the gravity and pressure turns this into metallic hydrogen. Metallic in the sense that it starts behaving as a superconductor. This critical point metallic ocean likely extends most of the way down towards the centre, giving Jupiter a substantial magnetic field. Intense reactions further down power violent weather in the planet's 500 km thick upper atmosphere. We can see swirls and bands in brilliant detail, and aurorae much more powerful than anything on Earth. But the most iconic feature on Jupiter is its Great Red Spot, a storm 3 times larger than the Earth, which has been raging for hundreds of years. Wind speeds within this storm can reach up to 600 km per hour, much more powerful than any wind current on Earth. Cosmic cyclones like this one occur within the planet's central belt and become raised above the rest of the atmosphere by a few dozen kilometres, quite literally resembling a teenage spot or pimple. We exist at a good time to observe this spot on Jupiter, but they can occur on the other giant planets too, including on the other gas giant planet in the solar system, Saturn. Saturn was the next planet to form after Jupiter, and while similar in some respects, it is different in many others. Saturn is thought to be composed of a dense iron and nickel core surrounded by rocky material, which has been enveloped in liquid hydrogen, like Jupiter but smaller and much lighter. Ammonia crystals in the outer atmosphere give it its rich yellow appearance. Despite being the second largest planet in the solar system, it is also the least dense planet, and the only planet less dense than water. Whereas Jupiter has a colourful cascading tapestry of winds on its surface, Saturn appears to be slightly more isotropic. Like Jupiter, Saturn formed sufficiently far away from the Sun, beyond the snow line. When Saturn was young, it collected rocky and icy material until it was a planetary body about 20 times more massive than the Earth, and when it reached this mass, it began pulling in leftover hydrogen and helium. Trillions of tons of gas enveloped the planet, transforming the surface under pressure 10 million times stronger than on Earth. Today, the planet is mostly hydrogen and helium in a variety of forms, powering phenomena such as liquid diamonds and helium rain further down. Like Jupiter, this weather has grouped into impressive systems, most notably its beautiful hexagonal structure at its north pole. But the most striking feature of Saturn is not on the planet itself, but the brilliant ring system surrounding it. All 4 of the gas giants in the solar system have a ring system, but they are much thinner, darker and fainter, and so we didn't know they existed for a long time. Saturn's rings, on the other hand, are easy to spot, visible from Earth in great detail, and so we noticed them as soon as we found the planet. They extend about 300,000 kilometers across, but are only about 9 meters thick on average. The fact that they are so dazzling and pristine compared to the other giants tells us a lot about how they formed and when. Saturn itself is billions of years old, but in comparison, the rings are only about 100 million years old. If they were any older, they would appear dustier. This probably means that, about 100 million years ago, one of Saturn's icy moons got too close to the planet and was shredded up into trillions of pieces of icy material, which fell into orbit along Saturn's orbital plane. This created the awesome rings, the essence of a dead, icy moon, reborn as one of the most bedazzling sights in the solar system. These rings also get a little bit of external help in staying so brilliant, as they are regularly replenished by cryovolcanic explosions on Saturn's moon of Enceladus, which ejects fresh icy material into space, which falls into orbit along the rings. Saturn's rings would not be possible within the inner solar system. It owes them and many of its other features to its distant location. But further out than Saturn lie the most distant and coldest worlds, the ice giants. Uranus is one such giant. While not as massive as the gas giants, it is 4 times the diameter of the Earth, meaning you could fit Earth inside more than 60 times over. It is thought to have a core made of magnesium silicate. The remaining 80% of the planet is mostly contained inside a layer of water, ammonia and methane, and the methane on the surface is what gives it its blue appearance. Unlike Saturn and Jupiter, Uranus's surface is particularly blank and featureless. Its surface covering obstructs the processes below, meaning the planet emits barely any heat back out into space, giving it the coldest surface temperatures in the solar system of -224 degrees. Uranus orbits the Sun 20 times further away than the Earth, and is the only planet to do so on its side. Planets usually orbit along the same plane and in the same direction because of the direction and motion of the collapsing cloud which formed the star and its system. But unlike the other planets, the Uranus system, including its faint rings and dozens of satellites, all seem to orbit on their side. Scientists think that this orientation is due to a collision with another planetary mass object, the impact of which tipped the entire system over on its orbital plane. Thus, its 13 faint rings appear vertical over the planet. These rings are kept in place by Uranus's 27 known moons, specifically its shepherd moons, Cordelia and Ophelia, small satellites which orbit either side of the ring system, exerting counterbalancing gravitational influences that keep the ring's matter in place. Finally, we come to the most distant giant of them all, Neptune. It is similar in size to Uranus, and despite being further from the Sun, it is a much more volatile world. Neptune has the most extreme weather found anywhere in the solar system, and great cyclones play out on its surface, including spot-like storms similar to the ones on Jupiter, but with much more aggressive wind speeds. Neptune records the highest wind speeds of anywhere in the solar system. With no landmass or surface to slow down currents, winds can climb to over 2,000 kilometers per hour. Out here, it is so cold that nitrogen freezes on the surface of its moons, but Neptune's interior is anything but cold. Its outer atmosphere consists of frozen methane crystals mixed with hydrogen and helium, becoming much more pressurised the deeper into the planet you go. Deep down, the interior temperature climbs to thousands of degrees, creating a liquid ocean 2,000 times deeper than anything on Earth. While we expect similar processes to be going on within the two ice giants' interiors, Neptune emits more heat back out into space than Uranus, giving it a slightly higher surface temperature, despite being further from the Sun, and we aren't actually sure what the source of this additional heat is, one of the many mysteries cloaking this fascinating world. So those are our 4 gas giants. They are huge and inhospitable, each with their own characteristics and special properties. But with all that considered, what could lie beyond our solar system, elsewhere in the galaxy? When searching for extrasolar gas giant planets, there was a time when we expected to find them only on the outer reaches of star systems. The solar system's arrangement today is surprisingly neat. The rocky planets are on the inside and the gas giants on the outside. And so, for a long time, we thought that was the natural order of a planetary system, with the gas giants needing to form further out, and perhaps this may be true to some degree. However, when we began looking to the stars, we realised that the arrangement of other star systems is very rarely this neat. Gas giant planets can be found scattered throughout their respected systems, from the cold and distant giants like Neptune to massive torrid worlds which orbit closer to their star than the Earth. The latter was the first type of extrasolar planet ever discovered, classed as a hot Jupiter. As the name suggests, hot Jupiters are similar to Jupiter in size and makeup, but they orbit their parent stars very closely, within about half an astronomical unit. Some orbit even closer. Approximately 1/6 of all exoplanets discovered orbit their star at a distance of about 0.1 astronomical units or less, so 10 times nearer to the Sun than the Earth is. It is thought that hot Jupiters orbiting at this distance formed further out, beyond each system's respected snowline, before migrating inwards. Planetary systems tend to be much less stable than our solar system, especially when you have one or many of these massive Jupiter-like influences barreling round in an eccentric orbit. Just under 1/10 of all stars have at least one Jupiter-like giant with an orbital eccentricity. This migration could wreak havoc on the arrangement of a star's planetary system, potentially ejecting planets and causing them to become rogue. The best known hot Jupiter is 51 Pegasi b, also known as Bellerophon and Dimidium. It was the first extrasolar planet orbiting a star similar to the Sun to be discovered. It is about 50 light years away, and while it is about half as massive as Jupiter, it is almost double the size. It orbits its parent star about once every 4 days, which is about as near to a star as you're likely to find a planet like this. Any further in, and the star's stellar emissions would fry the giant, stripping back its gaseous atmosphere through the process of hydrodynamic escape, exposing the core. What you would be left with is an old, dead gas giant centre called a Chthonian planet, but these are still a hypothetical type of planet. What we do know, however, is that gas giants thrive better beyond the snowline of a star system. This brings us to our next type of planet, a gas dwarf, better known as a Mini-Neptune. These planets are named as such because they have masses and compositions closer to Neptune than Jupiter. They form from large rocky cores which have accumulated thick coverings of hydrogen and helium, giving them a diameter between 1.5 and 3 times the diameter of the Earth, but less than Neptune. These planets house deep layers of ice and rock, and perhaps liquid oceans of water and ammonia. Hot gas dwarf planets exist, but they are somewhat rarer, as they are much more prone to the hydrodynamic escape of their atmosphere when orbiting close to their parent star than Jupiter-like planets. As such, Mini-Neptunes are generally found further out, beyond the snowline where ices can exist. We found loads of these planets during the Kepler mission between 2009 and 2018. Kepler 138d is one such planet, the smallest known extrasolar gas dwarf being only about 60% larger than the Earth with a similar mass. This indicates either a considerable water content or a thick envelope of gas. Larger Neptune-like planets do exist, called super-Neptunes, which have a diameter of between 5 and 7 times larger than the Earth, but these planets are rarer as they require much more gas to form than gas dwarfs do. Mini-Neptune planets are much better suited to cold environments, as are planetary ring systems. As mentioned, ring systems exist to varying degrees around all 4 of the solar system's giants, and there are likely to be billions of planets out there with illustrious ring systems similar to Saturn. But of all these ringed planets, there is one which we have found that completely blew our minds, taking a ring system to an entirely new level. Discovered in 2012, V1400 Centauri is a planet orbiting a star about 430 light years away, surrounded by a ring system of epic proportions. If you thought Saturn's rings were cool, just wait till you see this. See, I told you, they're bloody enormous. This planet is classed as a mega-Jupiter, but a more fitting name might be a mega-Saturn. Its ring system is over 200 times larger than Saturn's, comprised of 30 rings with a combined diameter of over 120 million kilometers. If this planet replaced Saturn in the night sky, the rings would appear larger than anything else, including the Moon. The rings are so large, in fact, that they totally eclipse the parent star from our perspective, blocking out a staggering 95% of the light emitted during transit. Normal gas giants without visible rings cause dimming by a fraction of a percent, so 95% warrants a big-ass object. Some speculate that moons may exist within these rings, having formed from the abundant material surrounding them. In the future, as the system ages, it is thought that these satellites will probably clear up most of the material in the ring system, which could lead to very large and even habitable moons like the ones we see around Jupiter and Saturn today, like phoenixes rising from the ashes of cold space dust. J1407b is an example of a cold super-Jupiter, generally the largest type of gas giant planet in the galaxy. They form beyond the snow line, and so some can grow to double the size of Jupiter and could become several times more massive. However, at about 13 times the mass of Jupiter, we expect a planet would begin treading the line between the largest planets and the smallest stars, namely a brown dwarf. There is no agreed mass limit at which point a gas giant becomes a small star, but 13 Jupiter masses is probably a safe bet. At this mass, the planet would not be able to fuse hydrogen like stars can, but could sustain the fusion of deuterium. This is where the idea that gas giants are failed stars comes in. There are two types of brown dwarf. One is a particularly large kind of free-floating rogue planet, which formed from a gas cloud like stars do, but wasn't able to sustain any kind of fusion. Thus, they are known as sub-brown dwarfs. Regular brown dwarfs, on the other hand, are heavier, about 13 times the mass of Jupiter, but below 80 times, at which point it would become a very low-mass red dwarf. While able to sustain some kind of fusion, brown dwarfs cool down and fade over time, eventually becoming too dim to be detectable. As such, there are probably billions of these brown dwarfs out there which we just can't see. The invisible ghosts of stars which might have been a kind of stellar purgatory, doomed to just fade from view silently. Gas giants are brilliant planets, and the term failed star just really doesn't do them justice. Brown dwarfs are the most reminiscent types of failed stars, but lower mass gas and ice giants began life as rocky cores and grew from there, destined to be planets from the very beginning. And while they might not shine like a star, they can support moons, ring systems, and beautiful extreme weather tapestries on their surface. They are capable of building, sustaining, and destroying planetary systems with their gravitational influence, and the gas giant planets of the solar system are probably more intertwined with our history and destiny than we yet realise. They are the godfather planets of the universe, and even as we learn more about them, they still continue to amaze and inspire us.